I'm Dan McCreary, and I'll be presenting a little bit on connecting healthcare. I should just give you a little background story on myself and how I got here. I've been studying the process of how organizations select databases for about 15 years. I'm going to really go into a little bit about the challenges we have in healthcare and why in the past we haven't picked graph databases for healthcare. And I think I'm going to then give you a picture of how graphs can help some of the problems. And towards the end, I'm going to go into a little bit of how we've developed processes to explain why graph to healthcare executives. And I think this is important because healthcare executives often are not the people who actually build these systems, they're the people who decide on which systems to build. So it's not a question of whether we understand it, it's whether we have the right metaphors to explain it to others, and I think that really speaks to some of the other presentations we saw from Hillary this morning. So just a quick background about Optum. If you haven't heard of Optum, we are effectively the IT division of United Health Group. Our mission is to help people live healthier lives and to make the health system work better for everyone. United Health Group is about $200 billion in revenue in 2017, over 250,000 employees, 42,000 IT employees, over $1 billion a year we spend in doing data analytics. We have over 3,000 people that have a title of data scientist or similar. And most of these people are using very, very traditional COBOL, mainframe, relational, and other systems. And the reason is we acquire a lot of healthcare companies that aren't on the bleeding edge, and we purchase them because of their data. Getting access to data is the central thing in building good predictive models. So my background is I'm now what's called a distinguished engineer and working in what's called the Advanced Technology Collaborative. The word collaborative is really important because our job is to get all these different organizations that have been acquired. United Healthcare acquires 20 to 30 new companies every year, and our job is to get them to all work together. My background is the NoSQL Now space, and I started a conference called NoSQL Now back in 2011, and my wife and I wrote a book called Making Sense of NoSQL. And ML and a lot of the people at Neo4j have been very strong supporters of our process of helping people understand the database selection process. So our book is really about the ways that organizations choose to store data. And there are about 6 basic high-level patterns. Relational on the upper left, where you have to put everything into tabular structures, and if it's in the third column, it has to be a date format. So it's a very rigid structure, and you have to model that before you put it in the relational databases. There's also analytical, that star schema, where you have all the facts in the middle, very good for aggregate reporting, but as they say, aggregation is not knowledge. And then there's the 4 what are called NoSQL patterns, key value stores, column family, graph, and document. And although we've studied a lot of them, I think one of the most underutilized today in healthcare is graph. And it's too bad because there's so many reasons that healthcare data fits beautifully and correctly into a graph structure. So our job then as a education organization that builds collaboratives is to work with solution architects. The main character in our book is a woman named Sally Solutions. And her job is to, given a business problem, what's the right architecture? Which one of these 6 patterns is right for her? And we want her to do this without bias. Bias means just because you read a blog article on something last week doesn't mean you should just try that. It means that we're looking for the fitness of the problem to the solution. And we want to do that before we start to select products. What I'm really seeing in the past is that many organizations are dominated by one technology, and that might be relational, for example. And they bring a single perspective to the solution space. Now what we're saying is to be competitive in the world with all this healthcare data that's changing so quickly, we need a diverse set of perspectives. And it's not just graph, but it's graph in combination with other things, key value stores, search engines, what we call multimodal systems that are really making organizations in healthcare competitive. So let's just talk a little bit about that process then. At the top row here, you see all of the different ways that we decide what are the requirements, what are the quality attributes of a system. And what we're saying now is that that bottom row, that middle box that has the architectural approaches, we want to now start to fill in with these different solutions. And this is a process developed at Carnegie Mellon. It's called architectural trade-off and modeling approach. And it really goes through and helps us rank these, do the analysis of the fitness, and understand those the trade-offs. And what we see is that certain things have critical requirements like a high availability or ability to manage complex rules. Those often fit very well into graph systems. All right, so let's just talk about the big problems in healthcare. When we think about it today, when we acquire all these companies, we get many, many different data silos. And some of these companies do completely different things. We might buy a company that does lab testing, another one that does MRI scan, another one that does ophthalmology exams. And then we look at all those the data from them, and they're completely different, right? High variability data, many diverse formats. And it's not just CSVs, it's JSON, XML, all the different formats that are coming across FHIR and RDF. All of those are different formats that we have to ingest. Healthcare also has a huge amount of complex terminology. All the names of every drug, every symptom, all the diseases, those all are appearing in patient charts. And we can't just use an off-the-shelf graph that has WordNet loaded into it. We have to have all our healthcare terms directly into that. We also are trying to build more trust. This is something that graphs aren't designed to do, but if you study blockchain and blockchain technologies, if you search for Google search for Optum and blockchain, you'll see we're doing a lot of work to make healthcare organizations exchange data in a better trusting way. We also have huge privacy issues. Everybody knows about healthcare privacy and HIPAA, how all of our systems that hold PHI, personal healthcare identifiable data, have to be very, very rigorously audited, and then the complex rules that get executed on those. We also wanted to start to do things like chatbots. Wouldn't it be wonderful if we can just open a chatbot and ask, hey, I want to know if my flu shots are covered by my health plan. And then we're also going to talk a little bit about machine learning and explainability, and then the scaling problems. All right, so the first thing is this integration challenge. So today, we have all these different systems, often running in different companies, built at different times with different technologies, and we think of them as just silos. And when people do analytics, they're usually only doing analytics on one silo. And when they merge data from multiple silos, it's very difficult to connect these. What we'd like to do is move to an area where everything is in one large healthcare knowledge graph, where everything's connected, where every person in one database is correctly connected. We call it entity resolution. Where we're integrating not just claims, providers, and remember, providers includes not just physicians, but every van driver that drops people off at a nursing home. Complex clinical systems, electronic medical records, all your prescriptions, all your allergies to certain drugs, your entire genome, and your entire Fitbit chain or your glucose blood monitoring systems. All of those things are contributing data to your healthcare individual patient record. And our vision is that all of these things will eventually fit in one large connected graph. And that's a long-term vision, but that's the goal that we're trying to move towards. And a lot of this is not just does it live in the graph, but all the things around it so that we can take your clinical documents and hook them up in the graph and find those words correctly using natural language processing. The other thing I want to just remind people of that when you think about data variability, if you think of relational databases, the classic thing that's stored in a relational database is something like a general ledger, right? Where every company has a general ledger, but the structure of that general ledger is very consistent. If you look on the other extreme side, the far right, clinical data has very, very high availability. So one of the questions I often ask organizations is, can you tell me about the variability of your data? what percentage of your records have exceptions. Sometimes even 1% of your records having certain things, they have to add extra columns to those databases, and those tables get very, very wide and then very inefficient. And sometimes we look at these structures and we see that we can see some variability today, and when we ask them what is variability going to be like in 5 years, they can't tell us, right? Very few people can predict future variability. How many people could predict what the structure of IoT, your Internet of Things devices, will be 5 or 10 years from now? It's not just going to be your Apple Watch, but it's going to be all these other biometrics. Every time you go to bed, your smart bed is going to tell you what time you wake up and how well you slept. So there's a lot of data that we can't even predict of what it's going to be like in 5 years. On top of that, we're trying to build chatbots. Typically somebody might want to open a chat in their healthcare system and saying, we're expecting a new baby, what's my coverage? And we need to have a chatbot that knows that new baby is associated with maternity coverage, right? And that really talks about taking words and alternate words and labels and linking them together. How do we do that? We do that in a graph. So we've built taxonomies for all of our benefit plans. Every time we see chats and questions come in, we can have people that add those to those taxonomies. And we use those taxonomies for two things. One is every time a new benefit plan is published, we can look at the words in that and we can associate it with the right parts of that taxonomy. It's called the document classification problem. And the second thing is we can start to look at the patterns in these graphs and see that as you go from baby and you can walk the tree and say that's closely related to the maternity care tree. So these are the standard ways that we're starting to use graphs to help us with our search. More chats that are answered, more search that are answered means fewer calls to our call centers. It costs companies typically $10 to pick up the phone and answer a question like this. But we can't do that today easily because everybody's benefit plans may be different. And what your deductibles are and how much you've paid in your copays might be different too. So those are very dynamic databases that we have to look up. So the question we're starting to ask is, what's the value of connected data? We had a group come up to us a while ago and said, well, we have these new genetic tests that we've never had before, and they're getting cheaper and cheaper. And we have these ICD-9 codes, diagnostic codes, that are associated with our medical records. What genetic tests should we be recommending? So that is, what are genes associated with these diagnostic codes? And the challenge we have is that we have some connections, but we don't have all of these. And so what we're seeing is that what we want to do is we want to add other ontologies that help us map these things together. And we find a lot of these ontologies out in the open linked data connection. So there's a system called the Unified Medical Language System that has a database of ICD-9 codes, and they're connected to concepts. We have genomics information. Those are connected to concepts. By putting these all in a graph, we can do the graph traversals, and we can recommend what genetic tests are associated with the right ICD-9 codes. So what we're trying to do then is build this connected healthcare network graph. And it has all these different objects that we see in the healthcare system. And this is just kind of notes that we had from a typical whiteboard session with one of our groups. And they were very interested in providers and the referrals of those providers and things like that. And then we'd often put this into some documents, and we'd meet with another group. And they say, yep, that's exactly what we want, but we're interested in our net promoter scores for providers. Our providers call in and they talk to an operator. That operator has had certain training, and we want to associate the training, how that training affects the net promoter score for our providers. So now we have to add more and more bubbles to these charts, and it just keeps growing and growing. So we really need to add all of the information about our help desk, all of the training, all those things need to be in a single graph. And we've never had all of that information tied together, simply because if you were going to do this in a relational model, it would be much too complicated. So our hope is that by putting things in a graph, we can make connections that have never been made in the past. So what are we moving towards? We're moving towards trying to store individual healthcare records or in individual knowledge graphs, and we want to then connect these things together. Now, if you have a diagnosis that has an ICD-9 code, we're going to maybe just store that code in an individual graph, but it's going to point to a very, very large graph that has all of knowledge about healthcare. So all of UMLS from public system, every time there's new papers that are published, that might add some more connections to that graph. So we're anticipating that there's going to be a rich set of pointers between records and this universal knowledge, and queries need to be able to access both of those, but we also need to be able to lock down an individual patient at a certain hospital so that if you're doing a query on them, you may not be able to see the others. There are some cases, though, where you're doing high-level statistics across multiple patient pools, and you're going to need to be able to do that. So we really need very robust role-based access control over all of our patient records and still allow them to be linked into this universal knowledge. All right, so what we're really trying to do is promote the thinking about new ways of looking at data where in the past our employees kept thinking the model that we have in our relational database is fixed. It's unchangeable. We can add one new column, but we have 10,000 reports, and if we change this one-to-one to a one-to-many, we're going to change the SQL for all 10,000 reports. So we could do that. We can add one column to our database, but it's going to cost us $500,000. And now we're saying, don't worry about that. Anybody should be able to add data. We should be able to harvest data from our call logs and add those things together, and we should be able to leverage public data sets. There's one story we asked. One of our call center people was saying, we have a lot of people in Medicare and retirement, and some of them don't drive. I would love to be able to recommend a provider that's near a bus route. And sure enough, yes, we can get access to public data about bus routes, and yes, we can rank every one of our providers based on how close they are to a bus route. That changes the value that we add, and we could do that because we could add bus route data in a way quickly, in a matter of days, which on a relational databases would have been a year-long project and multiple millions of dollars. So it's the agility of being able to add and add new data sets at any time and cross-link them that's helped us to really provide better value faster. All right, so let's just talk a little bit about when you're in a clinic and you have this big knowledge graph and you run some machine learning on that knowledge graph, and then it says, we recommend that you should do some diagnostic tests for diabetes here. And the doctor will say, well, why did you recommend that? Why didn't you recommend something else? And how can I trust you? What's the probability of this score? How can I correct that if you make a mistake? And that's what we're in today when we're using these traditional deep learning models. What we want to go to is a new architecture where instead of just having it a function, we want that machine learning process to update what we call learned explainable models. And these models are graphs that are updated as we do more machine learning, and that allows our physicians or our members to actually ask questions through an interface that looks much like Bloom. Why did you recommend this? Explain it. Show me the traces of the weights of why this is important. Give me some metrics. How do I give feedback into the system? And then that's going to promote trust. So in the healthcare system, we cannot use deep learning algorithms that don't have explanation, but we think that using graph models is going to be a much better way to build explainable AI. Another thing to look at is our model-based machine learning. If you study machine learning today, you take a lot of variables and you flatten that, you put it into your features, typically stored in a tabular function, and you have these things in your model that you have to then unwind. And you have all these complicated different algorithms that you have to use to unwind that flattening. What we're really trying to go towards is this idea of a single graph that encodes the assumptions that we make about that data. And what we're finding is that by using that, there's going to be a lot fewer algorithms that we need, and those are going to be much easier to understand. And so this is all called model-based machine learning, where graphs are an intimate part of that learning process. All right, so to wrap up, I want to just talk a few things about some metaphors that we've been using to explain this to management. And I just want to reach out and thank Dan Flavin for some of his great work helping us test these metaphors. I think they're actually being used in some of the Neo4j training classes now. So there's 3 metaphors that we've been using to help understand how graphs are very different. The neighborhood walk, the knowledge triangle, and the open world assumption. So let's just go through this. So start out with this one, the neighborhood walk. Let's say you lived next to a neighbor's house and you wanted to go over to your neighbor's house. How would you do this? Well, you'd open the front door, you would walk out the door, and you'd point to your neighbor's house and you'd walk there. It's very simple, it's very direct, and it's really a metaphor of how we store relationships by storing permanent pointers in a graph database. It is adjacent. Anything in the real world that has relationships, we store those as hardwired pointers, and it's one hop away. You don't need to consult anything else to get to your neighbor's house. How would we model that? We'd model that as a graph. Dan lives next to Anne. And so we see a very nice relationship in the physical world to something we can draw on the whiteboard. Let's contrast that with the way that relationships are calculated in relational databases. Relational databases do not store permanent pointers in memory. They actually, when you do a join, that where clause is actually a search. That search has to go into a central system to do that search. So the picture I want you to paint is, well, you can't walk over to your neighbor's house directly. You need to walk downtown to Index Town, right? And so what's Index Town? Well, it's a huge bureaucratic building, and you're going to go stand in line, and you're going to, it's like the DMV, takes a long, long time. When you finally get to the front of the line, you say, I want to get to 123 Main Street. And then they're going to plug that into a computer, and they're going to do a binary search. The more data there is, the slower that search is. Your data gets bigger. We have log n search performance. Hard to predict that performance because you don't know how much data you're going to have. And then they finally find that record and they give you the GPS coordinates. You plug those coordinates into your phone and then you can walk over to your neighbor's house. Okay? Now that sounds like a silly story, and it's designed to be silly. It's designed to be silly because I want you to remember it, and we've tested this. 2 weeks later, if you come up to somebody and say, can you explain the difference between graph and relational? If they can remember this story and they can remember the DMV, they'll try to express it, right? And they may not get it the first time. They have to go back and look at their notes. But this is a story that works. And we can do, you can test this. You can send out a survey 2 weeks after you do this training and ask how many people can explain it, all right? Do we do search when we do traversal in a graph? If they remember this story, they know it. No, we do drinks. If you think of one thing that makes a graph unique, it's understanding index-free adjacency, but nobody's going to remember that term. They will remember the story, all right? So try to use that story to explain it, especially if you have managers that want to understand the story, but they don't have the time and energy to repeat it and remember a complex technical term. The second story we use is called the open world scenario or open world assumption. And we borrow this term from the world of semantics and descriptive logics. You can go Google open world assumption. It means something slightly different, but we're borrowing this term. So in the relational world, we have what's something called the closed world. Closed by the sense that everything is prohibited storing in the database unless you model it. Unless you create rules for it, everything is prohibited until you create a permission rule. You can only add data that you model, and adding that data may impact all your queries in the future. All right? That's bad. The good world is the one on the right-hand side, the open world. The open world solution is that everything is permitted in the database unless we put in a specific rule that prohibits that data from being used. And the thing that's different about relational and graphs that is so important is that when we create new vertices of a certain type, we also put types on the relationships between them. So our queries use those relationships. They don't use wildcards. Sometimes they use wildcards, and sometimes those are going to have impacts to those things, but there's a pretty small subset. In general, in the open world scenario, everything's permitted unless I have a rule. And what that means, and because of the way that we model things, if we write our queries correctly, we can add new data without disrupting our existing reports. And that makes all the difference in the world. That makes our graphs more modular, more open, easier to build, easier to test. The open world is really what gives us agility. So that's the second metaphor, is that open world. So the third one is the knowledge triangle. And the knowledge triangle is pretty similar to what we've seen in some of the other ones, where we have this low-level binary data at the bottom, a lot of numeric codes from the systems. Relational databases like to use a lot of codes. The lookup tables, the pick lists are all stored in IDs for fast lookup. On top of that, we have concepts, the nouns in our world. On top of that, we have knowledge, pattern, and relationships, the graph level. And on top of that, we have wisdom and AI. And wisdom and AI is, can we structure the knowledge in a way that can be reused across projects? So the way that our CIO looks at this is, we have spent a huge amount of money building data lakes in a lot of companies. Data lakes was a very useful mechanism for taking data out of our transactional systems, putting it in one place so we can query it over and over, and we're not going to disrupt our transactional systems constantly. It was a way to take the burden off of our slower relational databases and store it in a cheap way. But many organizations were sold a bill of goods about data lakes and HDFS as it's going to be a database itself. But when we put all those numeric codes, we couldn't have tools to decode them. Now what we're saying is that we need a whole new generation of tools, and AI and machine learning and complex rules engines, where we're actually using graph technologies to extract data from our data lakes, to put them into this disconnected nouns, but also verify it and make it consistent. And then from that, also pull it together and find new relationships, right? So this is the entity resolution camp, and there's some fantastic tools out there that are starting to get really, really good at entity resolution, where you can start to just look at this data and find it and make those connections. And then that last step is the very top of the thing. If you go and Google this concept of transfer learning, we're going to learn things in our AI models. We're going to capture them. We're going to put them in a spot that they can be reused so we don't have to do all that training. And then we're going to, on a base model, maybe it's images models, we're going to add models for specific types of images and then add customizations for that. In healthcare, we're going to have a whole set of reference data here about healthcare terminology. We are working very hard to make sure that we can represent all healthcare terminology in a uniform graph structure for all of our applications to use that. And that's an ambitious goal, but one of the things that is important, because right now we have literally hundreds of people within organizations that we've purchased that have already duplicated this data. And it's our job to try to bring all those things together. All right, so what's at stake here? If you have read the book of Why by Judea Pearl, it's a fantastic story about causality and how by building these things called causal graphs, we can make much deeper understanding of our data. The story on the left is this apocryphal story called the smoking gene. And it was promoted by a lot of tobacco companies, and it said, well, there's probably some gene inside of you, and it causes you to want to smoke. And it's kind of a coincidence that you also get lung cancer. But there's probably no direct relation between your urge to smoke and lung cancer. That just happens to be because it's caused by the same root cause. What we found out, unfortunately, almost 20 years later, is that we can understand causality between smoking and tar in the lungs and causality between tar and lung cancer. But we didn't get our causal graphs correct. And this is the same thing that we see over and over for every type of procedure that people are trying to get healthcare coverage from that may not be effective. What's the benefits of vitamins? What are the benefits of homeopathy and acupuncture and all those things? Our job as data scientists is to figure out which ones are the most cost effective, which ones have good outcomes, to take real world evidence from our claims and understand the effectiveness of certain drugs in the context of the people taking them. A lot of drug studies have been done only on 50-year-old males, but now we ask, what's the population for younger females? Right? So all of these things have different causality, and we have lots of data, but we need to store them in graphs and understand that to make sense. So data scientists really have to understand causality to really do this. As an employee of Optum, I'm not specifically allowed to endorse any specific companies, but I do want to mention that we had a lot of summer interns, and we let them pick a lot of different projects. A lot of them gravitate towards graphs. A lot of them actually made great process on their graphs, and you can see that a lot of them got certification, and they were really happy. And I think they're also leaving Optum to go back to school, to go back to their colleges and universities, and so many of them are also starting to look at graphs as a fundamental way to think and how to solve problems. So what I really want to do is I want to throw this out as a challenge to every engineer out there, that I think that graphs are going to be the foundation for helping us lower the cost of healthcare. But it's not just graph alone. We need people that know graph as that foundation and then are going to layer other technologies on top of that. We call these wicked problems in healthcare, where we have lots and lots of disconnected data that we want to put together and build all these things that will lower the cost of healthcare. We've seen very good presentations. Graph and natural language processing, graph and machine learning, graph and search and semantics, graph and search traversal, visualization, all these wonderful vendors out there doing graph visualization, distributed systems, high availability, security, statistics, and causality. So it's not just graphs alone that are doing this, it's really other technologies that work with this. So I think that's what I wanted to cover today. We have a few minutes for one or two questions. And if people are interested, I do have this deck. I'll send it out to you. I should have mentioned at the very end, I do have a few slides on what I call our cognitive biases when we're picking databases. And we go through these in some of our other presentations to help your executives. So each of these has a little story behind them about how people thought they were being objective, and we really challenge them. They say, is this really helping matching? Those things can all be described in helping your organization be more objective. So any questions? Yes, go ahead. Right, yes, that's true. They say that good relational databases cache that information. Very often it doesn't happen.
It's cached, but you type it in if
yeah.
you put the SQL statement.
Right, exactly. Yep, it forgets it. Good point, yeah. Dan, question?
Just going to ask you to comment on further interpretation.
True, right.
I don't know if you want to comment on that or not.
So if I have a general ledger system, I want very, very consistent reporting, and I don't want people to disrupt that. I think we could do a GL in a graph, and we could limit the queries to the vertices that really mattered, and we could add other information, notes and things like that to it, and still not disrupt those queries. But I think your point is really that different databases have different benefits: consistency, reporting, ACID transactions, all those things. And as you scale up, you kind of turn down the dial on having consistent reporting because it takes a while for a node cluster to get in sync. So yeah, everything is different, and you'd look at the requirements and figure out what architecture to use. A question back there? Yeah, that's a good question. I should take a page from Thomson Reuters. Thomson Reuters has a product where they sell a knowledge graph, and they sell a permanent ID system, and they publish financial data in the terms of a graph. You can ingest that into your graph, and then you can associate things using their IDs. What we have with many healthcare standards, we have FHIR, F-H-I-R, and there's an RDF version of FHIR. But we're not at the stage where we can assign IDs. It's actually illegal to assign some patients permanent IDs in some states because of privacy laws, right? Because they don't want people passing around IDs that can de-identify data. So we do have a lot of challenges there. I think that what we have to do is understand how to balance the precise exchange of healthcare data with respect for people's privacy, and that sometimes those are in conflict. But I'd love, one of the best examples is provider data, right? We spend $2 billion a year in the United States just updating provider credentials to make sure that our providers have the right licenses to do the right procedures. And all of those things are done by hand in manual forms, and there's no incentive for providers to make sure their phone numbers or fax numbers or whatever are up to date. If we could do that once, use blockchain and other technologies to verify that information, we could make huge savings. So there are plenty of opportunities outside the firewall to make healthcare data transmission much better. And one of my passions is just getting everybody to use UMLS and SNOMED and using a consistent URI for every concept, right? That would be a good step in the right direction. Mayo Clinic has got a lot of material and papers online about what they're trying to do to get all their people to use consistent identifiers, URIs. And just because we're a property graph, by the way, doesn't mean that we can't steal concepts from RDF graphs, right? I love the fact that there's consistent IDs in RDF graphs. Let's use those in our property graphs and take all the good things and the inference patterns and bring them into our world. So, good question. Another one question over there?
Would you be where data is shielded?
Absolutely.
Maybe
Totally agree. Yep.
A way of circumventing.
Yep. Especially when you have data of questionable veracity, where you can't trust it. Maybe it should be in a special list where only certain scientists can see those relationships. Once again, access control lists are very important. And only when you go through certain quality standards would that be relevant in a patient's record, right? Because we don't know where it came from or whether it was authenticated. So yeah, I agree with your points. And I think that rules engines and access control lists and veracity queries on the graph could be helpers for that. Yeah, de-identification. Another question from the back there. Go ahead.
I've spent a lot of time on the types of analysis.
Absolutely, yes. So patient journey is a really important use case where when a call comes into a call center, we'd like to know every event that happened to that person in the past that got them to that point in time, including every email that was sent to them, every EOB that they called on, questions they've had in the past, questions that a provider might have asked about coverage for that patient and things like that, eligibility things. So all of those things are part of that patient journey. And in the past, our systems were so constrained, we only loaded about 10% of that eligible data. And so what we're trying to do is dramatically expand all the data points and tie it in together to see how we got to an endpoint from things. And what that means is that we have this concept of next best action, a patient journey. If they called confused 10 times about an EOB, we need to know that and contextualize that when we're answering questions on the phone. Not everybody is fluent in English and has all the understanding of the healthcare system that we have. And so that adding more data to the patient journey helps us contextualize, especially in Medicare and retirement, where we get maybe 100 calls a year. And we need to know that we have to change the way that we address those answers. And caretakers, right? Caretakers is another good thing. Our systems today don't understand the fact that you may have a caretaker that helps you take your medicines and things like that. And if we get a call from a caretaker, that has to be a part of that patient journey too. So I think the answer is yes. The hope is that we load far more data and integrate it together in our call centers. The challenge is everything we've talked about, scale and security. All right, we've got to overcome those. So great question. All right. So with that, I think we'll wrap it up. Thank you guys very much for coming, and enjoy the rest of the conference.